So RATEY is a way to graph rational expressions without having a calculator. So the R for RATEY is our roots, our x-intercepts. So the way we can graph or find these is we're going to take the numerator, we're just going to start with number 1, and set it equal to 0. So in this case, our numerator is just x, set it equal to 0, and that solves that one, right? Because it's just an x. However, we don't want to write it as x equals 0, because we're just talking about a point. So we're going to just say x-intercept, or the root, is at 0, 0. Of course, the y value would be 0, otherwise it wouldn't be an x-intercept. When we're talking about the A for RATEY, that's our vertical asymptotes. And so the way we find our vertical asymptotes is then we take our denominator from our equation. So in this case, we have the x plus 3, and we want to set it equal to 0. And then we want to solve for that x value. So when we solve for x, of course, we subtract 3 over, we get x equals -3. Now in this case, we do want to leave it in this form of x equals -3 because it is a line. So our x-intercept is at 0, 0, so we can put that on our graph. And we have x equals -3, which is a vertical line. So we'll go ahead and draw -3. So there is our vertical line at -3. The T of RATEY stands for tangent or together. The way we find this is we look at our problem. So our problem again is x over x plus 3. We want to look for multiplicities of 2. In this case, x is not a multiplicity, and x plus 3 is also not a multiplicity. The way that would work, we're going to see demonstrated on our second problem. So I'll get to that when we get there. So in this case, our t has nothing happening. So it's just a no. There's no togetherness, there's no tangents. Then our E, our end behavior, is dictated by the degrees of the first term in standard form. So in this case, our degree of our numerator is just x. So its degree is 1, because that's our first term. Our denominator, its first term, is also x. So its degree is also 1. So that means we have a balanced end behavior. So if it's balanced, meaning the degrees are the same, we're going to look at the coefficients on those first terms. Well, the coefficients on both of these are just 1. So that would be a 1 over 1 or 1. So our horizontal asymptote is going to be at y equals 1. So we have a horizontal asymptote coming across at y equals 1. And then the last thing, our y-intercept, we find the y-intercept by plugging in 0 for all of our x values. So I'm going to plug in 0 for my x, so that's going to give me 0 over 0 plus 3. Well, 0 divided by anything, or 0 divided by 3 in this case, still just 0, so our y-intercept is at the point 0, 0, which is what we already had for our x-intercept as well. So at this point, now we can do a sketch of our graph. We have one point, so we know as we graph this, our line is going to approach the asymptotes, but it's never going to actually pass it. So we've got this vertical one and this horizontal one, and we've got a point here. So we can sketch our line. It's going to approach the asymptote, but it's never going to cross it. Okay? So an asymptote means it's going to keep going forever and ever. This is going to go towards infinity, but it's never going to cross that line. It's never going to cross that asymptote. Again, it's going to approach that asymptote. It's going to go on forever, but it's never going to cross it. The T is going to dictate where my other side of my graph is going to go. So the T in the denominator part stands for together. If we had a multiplicity in our denominator of that x plus 3, which we do not, that would mean the lines would come together. In this case, we don't have that, so our lines on the asymptotes go in opposite directions. So that means we cannot have our line down here. It must be in this quadrant. And so our sketch of the graph is this. Okay. And again, we can check, plug it right into your calculator. And when we do that, we do get these lines. Okay? So let's do that again, but this time with number 2, 5 over x minus 2 squared. This is where we're going to have what we call that t, or that tangent or togetherness. So again, start with r. Take the numerator, set it equal to 0. So 5 equals 0. That is a false statement, meaning it can't be true. So in this case, 5 will never equal 0 because 5 is 5. So we do not have any x-intercepts, no x-intercepts or no roots. And then again, we look at our a, our vertical asymptotes. We want to set our denominator equal to 0. So we've got x minus 2 squared equals 0. Well, we can take the square root of both sides. That will get rid of the square. That gets us x minus 2 equals 0. And then we're going to add 2 across. So we're going to get x equals 2. So we have a vertical asymptote at x equals 2. And then that brings us to our t. So our t, again, is we want to look for multiplicities. Well, we have 5 on top, no multiplicity there, but we do have x minus 2 squared. So we've got 2 of those. And so with that multiplicity, we know we're going to have togetherness, or these 2 lines are going to approach our asymptote at x equals 2. So that means wherever these lines are coming, they're either both going to be going down at x equals 2, or they're both going to be going up at x equals 2. They're coming together. They'll never meet, but they're going to try. So that brings us to our e, our in behavior. Again, in behavior, looking at the first term, so we've got a 5 on top. And technically, if we have x minus 2 times x minus 2, we multiply those 2, we're going to get an x squared as our first term in our denominator. So in this case, our leading coefficient, or our top term on our top, is a 0 degree, meaning there's no variable, it's just a constant, and we have a degree of 2 in the bottom. So that means we are bottom heavy on this one. If we are bottom heavy, we're going to have a horizontal asymptote at y equals 0. So that is our x-axis, which also explains why we have no roots, because we're not crossing the x-axis anywhere because that horizontal asymptote. And then our y, again, is our y-intercept. Plug in 0 for our x values. So we got 5 over 0 minus 2 squared. Well, 0 minus 2 gets us a negative 2. Negative 2 squared is 4, so we have a y-intercept at 5/4. So there's our point. Now we have one of our quadrants, right? We know the graph is here. We can take our points. We're going to approach those asymptotes, but not cross. And our t is telling us we're together at that x equals 2. So our second point is going to be coming up towards that asymptote at x equals 2. So there's our sketch of our graph. Again, you can take some points, you can plug in 4 into your equation, and then plot that y value to get a more accurate sketch. But again, we're just looking for some basic points. Using RATEY, we can do that. And then let's look at our last one. We're going to look at number 4 as well. Number 4 has something happening from that activity that y'all did on your own. So if we look at number 4, we've got x squared plus 3x divided by x plus 3, x minus 4. So if we look at our r, again, setting our r, we want to find our roots. So we're going to take our numerator, set it equal to 0, and solve. So we got x squared plus 3x equals 0. We can factor out an x because they have that greatest common factor between them of an x. That's going to leave us with x times x plus 3. Set both of those factors equal to 0. We're going to get x equals 0 and x equals negative 3. So we should have x-intercepts at 0 and at -3. Then let's look at our asymptotes, our vertical asymptotes, or our A of rating. So we set our denominator equal to 0. So we have x plus 3 times x minus 4 equals to 0. When we set these equal to 0 and solve, we're going to get x equals -3 and +4. Just say those are x-intercepts, changing those to points. Because again, we have these vertical asymptotes. So here's where something stands out. We have a vertical asymptote at x equals -3. So we said we had an x-intercept there. We can't have an asymptote and an x-intercept at the same spot. And what would really happen is when we look at it, well, we have x times x plus 3 divided by x plus 3 times x minus 4. We have x plus 3 in both the numerator and the denominator. So those two things actually cancel each other out because we're dividing by itself. So our simplified version would just be x times x minus 4. And so when we have a term or a factor cancel out, that is where we get a hole in the graph. So at x equals -3, wherever we're at on that graph, there's going to be a hole there. Okay, so we got a hole at our x-intercept of -3, or the value of x equals -3. Okay, we've got a hole there. So just think of that. Hold on to that thought. And we'll deal with it when we graph our equation. Okay. So then let's look at our t. Oh, we do have that asymptote at x equals 4. So then let's look at our t. Do we have any repeating factors or multiplicities? Again, no. So there's none there. Then we can look at our e, our in behavior. If we look at both the top and the bottom, again, those leading terms are just x. So we've got 1 over a 1. So we've got a horizontal asymptote at y equals 1. And then our y, again, plugging in 0 for our x values. We've got 0 over 0 minus 4. So we're just going to get a 0. So again, our y-intercept is at the point 0, 0. And we already have that point. So then we can graph, right? Again, we're going to come down on this bottom part because that's where we have our intercepts. And then because we are not coming together, we're going to have our other line up top in the opposite corner. Now, remember we have that hole. So wherever we're at -3, we can just erase that part. And we're going to put it in an open circle to say we have that hole in our graph. That is how we graph our holes. And whenever we have those asymptotes, along with our x-intercepts, have the same value or they cancel each other out, that's how we do it on our rating. If you have any questions, email me back.